To reverse a mathematical operation, we traditionally rely on inverse functions, but the mechanics of trigonometry inherently resist this exact type of reversal. For any function to be mathematically reversible, it has to follow a strict axiom. It must be one-to-one, or injective. Geometrically, that means every output the function produces must map back to exactly one unique input. If you know the result, you can retrace your steps to a single starting point. The second requirement is that the function must be onto, or surjective, meaning it completely covers its defined range of outputs. When a function is both injective and surjective, we call it bijective. That is the strict prerequisite for any mathematical inversion. So let's test our standard trigonometric functions against this ironclad bijectivity rule. This graph plots the standard sine wave across multiple periods. We test its geometry using a horizontal line sweeping down the y-axis. It hits the curve at multiple points simultaneously, revealing a many-to-one relationship. Isolating an output of 0.5 traces back down to pi over 6, 5 pi over 6, and 13 pi over 6. A single output traces back to infinite inputs. Because of this infinite repetition, natural trigonometric functions are uninvertible as they exist. To create a true functional inverse, we must physically alter the underlying structure of the mathematical wave itself. When an infinite function fails the strict bijectivity test, mathematicians use a specific workaround. They perform mathematical surgery. We call this domain restriction. We deliberately slice the function to isolate a segment that never repeats. For the sine wave, we need to scan along the x-axis and find a continuous slice that captures every possible output from -1 to +1, without a single y value occurring twice. We isolate the exact segment spanning from -pi/2 to +pi/2. Running the horizontal line test across this newly isolated segment, the line intersects the curve exactly once at every output. There are infinite slices we could choose that satisfy this rule, like pi/2 to 3 pi/2, but mathematical convention dictates we select the interval spanning the origin. This universally agreed-upon interval is known as the principal value branch. Now that we have a bijective segment, we can perform the actual inversion by geometrically swapping the x and y axes. By reflecting this restricted curve perfectly across the diagonal line where y equals x, we generate our new inverse function. The inverse sine function now formally exists. Its domain is restricted to -1 to +1, and its range is -pi/2 to +pi/2. We explicitly sacrifice the infinite domain of the periodic wave to forge a single, reliable mathematical tool. The question now is whether we can take that precise interval used for sine and apply it directly to all other trigonometric functions. Let's see what happens if we restrict the cosine function to that same -pi/2 to +pi/2 window. This creates a symmetrical U-shape entirely above the x-axis. Within this specific box, cosine returns the same positive values twice and misses all the negative values completely. Our horizontal line drops down and hits the curve twice. It fails bijectivity. To fix this, we slide our restriction window along the x-axis to capture a valid one-to-one mapping. Sliding right, we lock the cosine domain from 0 to pi. We then reflect this new segment across the axis to derive inverse cosine. The tangent function requires a slightly different approach. This graph plots tangent, which is naturally structured as a series of repeating S-curves separated by vertical asymptotes. Tangent naturally isolates itself into clean branches right between -pi/2 and +pi/2. But there is a critical notational difference here. For inverse tangent, we use parentheses to denote an open interval. Because the tangent function physically approaches infinity and is undefined exactly at those boundary lines, the boundaries themselves cannot be included in the inverse range. We face a similar boundary issue when we look at the reciprocal trigonometric functions, starting with cosecant. Functionally, cosecant is defined as 1 divided by the sine of x. If we map the diverging curves of cosecant directly over our restricted sine interval, we hit a mathematical wall. Right at the center, sine equals 0, and because you cannot divide by 0, cosecant cannot exist at that exact coordinate. To prevent a divide by 0 error, we have to physically extract the origin from the domain. In Foreman's set notation, we write this as the closed interval from -π/2 to π/2 minus the set containing 0. This exact preventative logic applies to the secant function as well. Secant relies on the cosine interval from 0 to π, but we must explicitly subtract the point at π/2 where cosine crosses 0. Reciprocal inverses are highly specific constructs. They rely on the precise algebraic extraction of undefined points to maintain their structural integrity. We can aggregate all 6 of these newly engineered inverse functions into a single unified system. This matrix outlines the definitive domain and the resulting principal value branch for every inverse trigonometric function. It looks like a dense list of arbitrary rules, but as the 19th century mathematician Felix Klein noted, mathematics, in general, is fundamentally the science of self-evident things. Memorizing this matrix is secondary to understanding the bijectivity requirements that built it. Once you know why the restrictions exist, the rules become self-evident. But before using these tools, there is a major operational warning to cover, a notation trap that frequently derails students. Inverse notation and exponent notation can look exactly the same, but they perform completely different operations. When the -1 superscript is attached directly to the function name, like sine inverse of x, it specifically designates our restricted mapped inverse function. However, if the -1 is placed outside parentheses, like the quantity sine of x to the -1st power, that creates a reciprocal fraction. That is just 1 over sine of x, which is simply cosecant. Standard mathematical practice dictates that when evaluating an inverse function without a specifically requested branch, we universally default to the principal value branch. By bending infinite periodic waves into these precise, bounded tools, we create the structural foundations required for advanced calculus.